So the next speaker, it's a great pleasure for me to introduce her, is Alice Garbagnati from Milan. And she will talk about projective models of Nikulin orbifolds. So the title stay there.
Okay, shall I start? Okay, so this is a joint work with Chiara Camere, Gregor Kapushka, and Michael Kapushka. Okay, so what is the idea of this work of this talk is to describe something about the hyperketer orbifolds. The main point is that, as everybody knows, there are very few examples of hyperketer manifolds, and so at a certain point one decides to consider not just hyperketer manifolds, so not just something which is smooth, but to accept also to study something which has some singularities, not so bad, which are similar to an hyperketer manifold. So the starting point is that I want to define what a hyperketer orbifold is. So the definition is the following. X is an hyperketer orbifold, or if you prefer, an irreducible holomorphic symplectic orbifold. If, of course, it has to be an orbifold, which means that locally it is isomorphic to C at a certain power n mod out by a group, a finite group. And of course, when you consider the group to be the identity, you have something which is locally smooth. Then you want that the codimension of the singular locus of X is bigger, in particular is bigger than 4, is bigger than or equal to 4. And then now we have the part where we are requiring something related with the conditions to be hyperketer. We want that on the smooth part of our manifold, we want that it is simply connected and there exists a non-degenerate holomorphic form, so essentially a symplectic form omega, such that H20 of X is generated by omega. Okay, so of course, if you now assume that your X is smooth, of course, it goes inside these definitions and you find the definitions of a hyperketer manifold, the standard definition of a hyperketer manifold. And if you consider hyperketer manifolds, the easiest cases that you can consider is the ones of a surface, and we want to be inspired a little bit to what happens for the surface. So S is a K3 surface, which means this means that it is an hyperketer manifold of dimension 2. And there is a way to produce, how can I say, new K3 surfaces of different K3 surfaces starting from a known K3 surfaces, which is considering symplectic automorphism on K3 surfaces. So I just want to describe some results which are known for the K3 surfaces, just because these are the results which we want to generalize in either dimension. So the point is the following, so that I'm going to say this S is a K3, surface, and iota is an involution on S, so it is an automorphism of S whose square is equal to identity and who acts trivially on the second, on this symplectic form that you have, that we have on the K3 surface, and then we can consider S over this involution. This is a singular manifold. It is singular in 8 points, and we can consider the minimal resolution. Here we are in the context of surfaces, so everything is very well known, and the minimal resolution is something which is clearly defined. And we find something which is smooth, because we are considering a resolution, and it is also a minimal surface, and the point is that it is another K3 surface. So considering quotients by symplectic evolutions and also by symplectic automorphism of higher order, but we are not interested, is a way to pass from a K3 surface to another one. And we will want to reproduce a similar argument in higher dimension. So first of all, I would like to recall what is known about these K3 surfaces, which is the ones which admits a symplectic involution, and another K3 surface, which is the one obtained as quotients of the ones which admits a symplectic involution. So we have the following theorem, and it's very difficult to say who is the author of this theorem because I'm just recap lots of results, so I have to put here lots of names. Sarti, and later there is a paper by me and Alessandra. And putting all these results together, one obtains the following. So let us, as above, so S is a K3 with Y, with iota. Iota will be always a symplectic involution, so with a symplectic involution. And let us assume that S is generic among the K3 surfaces with these properties, which means that the Picard number is the minimal possible. Then the Neron-Severi group of S is known to be equal to E8 minus 2, which is a certain lattice. It doesn't matter if you don't know what is this lattice. And S is non-projective. But the main point is not just that one, but it's also the fact that we know who is the Neron-Severi group of the quotients, or better, of the resolutions of the quotients of S by iota, which is a lattice N, which is called the Nikulin lattice. It doesn't matter who is it, but the main point is that the Nikulin lattice N is not isometric to E8 minus 2. And for this reason, we know that S is not isomorphic to the singularization of its quotient, at least if we consider S generic. And this is the reason for which I wrote here that considering the quotients by symplectic involutions is a way to produce another K3 surface starting from 1, which is given. And of course, this is a nice result, but we are not very satisfied by this result because these surfaces are not projective, and we want to do algebraic geometry project. We want to study projective manifolds, and so I have more specific results if S is projective and generic among the K3 surfaces which are generic, which are projective, and admits a symplectic involution iota. In this case, we have that the Neron-Severi group of S could be of two different types. It could be either isometric to a lattice, which is called the lambda 2D, and which is nothing but the direct sum of 2D plus the lattice that we already mentioned before. Here we are assuming that D is a positive integer, and in this way we have a positive class in the Neron-Severi group, which allows us to deduce that our K3 surface is projective, or either this one, or we have another possibility, which is that our Neron-Severi group is another lattice, which is called lambda 2D tilde, which is a specific over lattice of lambda 2D. I don't want to describe it now, but of course the description is known. So we have a complete classification of a Neron-Severi group which could appear, and we have that the Neron-Severi group determines uniquely also the transcendental lattice of S, and so the family of lattice polarized K3 surfaces with a given property, so the families of S, and the dimension of each of these family is 11, but it's not so important now. Moreover, we have another part of the results, which is the following one. So if I know who is the Neron-Severi group of my K3 surface S, which admits a symplectic involution, I'm also able to describe the Neron-Severi group of equations of its desingularization. Indeed, in this case, we have a certain lattice, which is called gamma D, and which is a direct sum of D plus N, where this N was exactly the Nikulin lattice that I mentioned before. And in this case, I have that the Neron-Severi group of S over iota tilde is a specific overlattice of one gamma, in particular gamma 4D, and you see that there is a certain relations between this polarization that we have here and the polarization that we find here. In any case, we are able to relate completely the family. Also in this case, the non-severe group of the family determines uniquely the transcendental lattice, and we have a complete description not just of the families of K3 surfaces which are projective and admit symplectic evolutions, but also of a family of their quotients. So this is what is known for the K3 surfaces, so for the cases of surfaces, and we want to reproduce or find similar results in higher dimension. And of course, we will see that there are some differences. So our setting will be the following. First of all, we restrict ourselves not to all the possible Hyperketer manifolds, but to some very specific Hyperketer manifolds. So X will be an Hyperketer manifold of dimension 4, and we know that there are essentially two ways different to produce the Hyperketer manifolds of dimension 4, which are not deformation equivalents. We consider just one of these two possible constructions, and we want that X is of K32 type, which means the following is deformation equivalent to something, so to the Hilbert scheme of 2 points on a K3 surface. And I don't want to describe it as a Hilbert scheme of 2 points, but I want to give a slightly different description in terms of quotients. So I consider a K3 surface as I consider the product of S time itself, and then I consider an automorphism which switches these two pairs of S, and then I can consider the quotient as times S over sigma. This is singular along a surface, and so I blow up the singular locus, and I find something which is smooth and is denoted by S2, and we will prove that this is an Hyperketer manifold of dimension 2. And of course, now what is happening is that here we are blowing up something. So we are introducing a certain divisor which is related to this divisor, so the exceptional divisor. To be honest, there is a certain object which is delta, which is 1/2 the exceptional divisor. In any case, we are introducing something which does not appear here, and this object is, of course, contained in the second cohomology group of our S2, but is also contained in the non-severe group of S, because essentially it is the exceptional divisor. So it is an algebraic class. It is supported on a hypersurface here. But there exist some deformations of X such that delta is still contained in the deformation X, such that delta is still contained in the second cohomology group because the deformation doesn't change this group, but it is not contained in the non-severe group of X. In this case, we have an Hyperketer manifold which is of K3 type, but is not really the Hilbert scheme of 2 points on a K3 surface. So it's not really obtained as the singularization of a K3 surface by the singularization of the quotients of a product of a K3 surface by itself by an automorphism, but it's just deformation equivalent to this. Then I would like to consider something else. On Y, on X, I suppose that there is an involution. So iota is a symplectic involution on X, which means that it preserves the symplectic form, which is that omega that I defined before. And what is known about these pairs X and Y is the following. So known results. Iota star X on the second cohomology group of my Hyperketer manifold, and this second cohomology group is endowed with a Bovil-Bogomolov form, which is a symmetric bilinear form, and in this way, this is sorry, I write and then And in this way, we have that this object has a structure of a lattice. So since I have a lattice structure, I can describe this lattice, which is uniquely determined by the fact that X is of K32 type, and its second cohomology group is this one, where this essentially comes from the second cohomology group of H2SZ, because it is isometric to the second cohomology group of a K3 surface, and this is essentially comes from this new divisor that we introducing when we blow up. So as I said, that we have an action of iota on this lattice, and the action is known. Indeed, it acts as the identity on this free copy and as the identity on this -2, and it switches these two pairs of EAD. This is a result due to Mongardi, in the sense that Mongardi proves that this action is essentially unique by generalizing a previous result given by Nikulin, who studied the K3 surfaces cases, and the description explicit of his action is given by Morrison in the sense that Mongardi proves that the description is exactly the same, the action is exactly the same as the one that you have in the case of a K3 surface and on this part of a lattice, and then is the identity on this extra part. So since Morrison described the action for the K3 surfaces cases, Mongardi proves that the action is that one for the case of a hyperketer manifolds of K32 type. So we have this action, and there is something else. We know the fixed locus of iota on X, which consists of a K3 surfaces and 28 isolated points. And this is due to Cambre and Mongardi. And then what I would like to do, of course, is what I did before. For the K3 surfaces, I consider a K3 surfaces with a symplectic involutions, and then I consider the quotient. So I would like to do exactly the same thing. So here I consider the quotients of X by this iota. Here I would like to call this map pi. And this object is singular in the image, so the singular locus of X over iota is pi of the fixed locus of iota on X. And so it consists of a K3 surface and 28 isolated points. Okay, so before what we did was to resolve the singularities, just blowing up the singularities. In this case, we can do this only partially, in the sense that I have X, I consider the quotient X over iota, and then I blow up not all the singular locus, but just the singular surface. And I obtain something which will be called Y. And the main point is that this Y is a Hyperketer orbifold. And it will be called a Nikulin orbifold. So a Nikulin orbifold is an orbifold which is obtained as a quotient of an hyperketer manifold of K3n type by a symplectic involution. So let us try to understand why we want to blow up the surface and why we don't blow up the points. Of course, I can blow up also the points. And if I blow up everything, I find a smooth manifolds. But the point is that on X, I have a symplectic structure which is preserved by iota. This symplectic structure induces a symplectic structure on the smooth part of X over iota. And when I blow up something, if I would like to find something which is symplectic, I have to extend the symplectic form on the smooth part of X over iota to the full manifolds. This is possible when I blow up the singular surface, and this is because essentially there exists a Crepant resolution of the singularities which appears along the surfaces, but it's not possible when you try to blow up the points. If you blow up the points, you find something which is smooth, but does not admit a symplectic structure. And the problem is essentially that the points here are terminal singularities. So they come from the diagonal action of the matrix minus the identity. And so this kind of singularities does not admit a Crepant resolution. Okay, so we introduce this partial resolution. And after this, we have an Hyperketer orbifold, and you can check that all the properties of a Hyperketer orbifold are satisfied because this is a quotient, so it is an orbifold. it is its singular locus has codimension 4, and there is a symplectic structure on the smooth part. This has to be proved, and also the fact that it is simply connected has to be proved, but is known. I would like also to underline that when I blow up this singular surface, I am introducing a divisor, which will be called sigma. Okay, so now we have our object, which are these Nikulin orbifolds, and we want to play the same game that we played before with the K3 surfaces. So now what we understand is that if we start with some Hyperketer manifolds of certain type, and we consider involutions, symplectic involutions on these Hyperketer manifolds, then we can obtain something on the quotient, which is not an Hyperketer manifold, but it is at least an Hyperketer orbifold. And we want to play the same game that we played before. So what is known for the K3 surfaces is both the descriptions of the family of the K3 surfaces which admits symplectic involutions and the relations between these families and the families of the quotients. So what we want to do now is exactly the same. So the first theorem that probably need a new page is the following one. So X is an Hyperketer manifold of K32 type. So X is of K32 type, and in the following will be always like that. So probably I don't write this every time with symplectic involutions. Then, if X is generic, then the Ronsevery group of X is E8 minus 2, and in this case, X is non-projective. If X is generic among the projective Hyperketer manifold of K32 type with symplectic involution, then there are 4 families. X is contained in one of the following 4 families, and this is a little bit different with respect to what happened before for the K3 surfaces. I would like to call these families A, B, C, D. In the first case, the Ronsevery group of X is given by our lattice, the same that we used for the K3 surfaces, lambda 2D. And also in all the other 3 cases, in all the first 3 cases, we are in the same situation. Here we have some conditions on the parity of D or something else. So if I'm writing just this part of the theorem, there is no reason for which you understand why the family A, B, and C are not the same. And the point is that in this case, the Ronsevery group does not determine uniquely the transcendental lattice. So I have to write also the transcendental lattice in order to determine the specific families of the K3 surfaces, which means essentially that I'm fixing an embedding of a Ronsevery group of X in the second cohomology group. And it's not really important what the transcendental are. I just want to write down them just in order to show that they are not always the same. So if you look at a little bit the family B and D, they have the same transcendental lattice, but a different Ronsevery group. And the family A, B, and C has the same Ronsevery group, but different transcendental lattice. So these are really different families. And this, we have something else, something like this. And here we have a lattice which is called KD, which is not important what it is. Okay, so in any case, so essentially we have 4 different families. We have infinitely many families because, of course, we have a family for each D. But we have 4 different ways to construct these families, and all of them have dimension 12, which is one more the dimension of the K3 surfaces with a symplectic involution. Okay, so we have a complete description of these families, and now we want to do what is done before. So we want to relate these families with families of Nikulin orbifolds, so of the quotients of this Hyperketer manifold by a symplectic involution. And one again, I have to cite some known results on Y, because the main point is that Y is not the same object as X, is not an hyperketer manifold, so it has no, for example, the same cohomology group of an hyperketer manifold, just because it is not an hyperketer manifold. And the first result that I want to mention is that H2 of Y Z can be endowed with a form which is essentially the ones by Boville-Bogomolov, in the sense that the biggest part of this form is induced by the ones of Boville-Bogomolov on X, and this form makes these objects in a lattice, and as a lattice this is known, it is equal to U multiplied by 2 3 times plus E8 minus 1 plus minus 2 plus minus 2. And this result is due to Menet. And I would like to explain a little bit how one can understand this kind of result. So I have a map which is a quotient map between X and X over iota, and then I have a map which is pi lower star, which maps the second cohomology group of X in essentially the second cohomology group of this orbifold. And this map is very well known because it is induced by the action of iota on the second cohomology group, because it is induced by the quotient by iota. And so, since I said that iota acts exactly as for vacatory surfaces, since this map is very well known and studied by Van and Sarti, in the cases of vacatory surfaces, one obtains more or less all what is needed here. And the point is that here you have that pi lower star of U plus U plus U plus E8 minus 1 plus E8 minus 1 plus minus 2 is equal to, here the action of iota is the identity, and so here this map takes one vector and it maps a vector to itself, but multiplying the form by 2. So here I find U multiplied by 2, U multiplied by 2, U multiplied by 2, and here I find minus 4, and here these two objects goes together and give me 1 copies of E8. But if you consider this one and this one, you realize that there is a missing classes. There is an extra class here. The rank of this lattice is bigger. And of course there is, because here I perform a blow up. I introduce a divisor sigma. So what Menet proved is that this Boville-Bogomolov form on Y computed on sigma gives me a class which has a self-intersection minus 4. Here we have a class that I want to call delta, and he also proved that delta plus sigma over 2 and delta minus sigma over 2 are contained in H2YZ. This essentially means that if I want to have a Z basis for this lattice, I have not to consider just this object and sigma, but I have to consider some rational linear combination with rational coefficients of this object. But now the very good news is that we have a basis of this lattice over Z. So if I want to compute the Néron-Severi group of Y, essentially I expect that it is the push down of the Néron-Severi group of X plus this lattice which is generated by sigma, because this one gives me the Néron-Severi group of a quotient, and then I have this extra divisor which comes from the blowing up that I considered here. But this result is true over Q and not necessarily true if I'm looking for a Z basis of these lattices. And the reason is that exactly written here, because sometimes you have to consider some linear combination with rational coefficients of the object that you find. In any case, we know who is this object, because this object, let us consider the easiest case. So the case where the Néron-Severi group is just a direct sum of 2D plus E8 minus 2, which means that this is generated by an ample divisor on X. And then what is happening is that when I push down all the Néron-Severi group, I just find the push down of L. And the reason is that here the action of iota is minus the identity. So there is nothing which is the image of this object inside the quotient. So what I'm saying is that in general, the generators of the Neron-Severi group of Y are these two objects, but sometimes I have to consider some linear combinations with rational coefficients. Apart from that, the computation is totally trivial. And I know if I have to consider linear combinations with rational coefficients or not, because I have a Z basis of the ambient space, so of H2YZ. And in this way, one proved the following theorem, which is the analogous of the other part of a theorem that I mentioned for the K3 surfaces. So if X is a K32 type Hyperketer manifold with an involution iota, and Y is its Nikulin orbifold, which means that it is the quotient of X by Y, and then we consider the resolution, the partial resolution, and X is in the family. I would like to recall that we have 4 possibilities for the family. So if it is in family A, then the Neron-Severi group of Y is something, is 4D plus minus 4 minus 4. In this case, the Neron-Severi group of X is lambda 2D. If it is in the case B, then the Neron-Severi group is something. It's not really important what it is, but it's something. In the case C, again, we have the same Neron-Severi group, but if I wrote here also the transcendental lattice, you can check that they are different. And if it is in the case D, then the Neron-Severi group of Y is D plus minus 4. So for example, in this case, I have that the Neron-Severi group is really generated over Z by the classes that I mentioned before. In this case, I have that the Neron-Severi group is generated over Z by this class, which is pi lowest star L divided by 2 and sigma. And in this case, I have something else, which is something like that. The sum of these two classes divided by 2. So I find everything I want in the sense that I am able to relate to each families of Hyperketer manifolds of K32 type which admits a symplectic involution its Nikulin orbifold by considering the families. And of course, why I have to explain why the Neron-Severi group changes of Y changes when I'm changing the family. Essentially, choosing the family, so the family of X determines an explicit embedding of the Neron-Severi group of X in the second cohomology group of X. Then I apply this map pi lower star, which is known, and this is always the same because it is attached to the fact that the iota has a unique action here, but this embedding depends on the family. And so in particular, the embedding of L inside the Neron-Severi group depends on the family that I am considering. And so when I am applying this pi lower star to my L embedded here, it's possible that the class that I find has to be divided by 2 to have a primitive classes here or not. It depends on how L goes inside this lattice. And indeed, this is the reason for which I find different Neron-Severi group considering different families of X. Okay, so now we have everything from the points of view of, from a lattice theoretic points of view and from the points of view of families which are attached to these Hyperketer manifolds and to this Nikulin orbifold. And I would like to say something about the projective models of both these objects. So I started with X, and let us assume that the Neron-Severi group of X is the easiest possible lattice. Otherwise, everything is similar, but it's a bit more complicated to write down. So here I have an ample divisor, as I said, which is attached to this positive class. So here I have a map which maps my X to the projectivization of a spaces of a dual of a spaces of a section of L. And I want to call this vector space V. Since iota X has the identity on the class of L, so it maps the divisor L to the divisor L, iota acts in a certain way on the spaces of the sections of L. And so, of course, it acts also on the spaces, on its dual spaces. And the action here, I mean, I have an involution which is acting on a vector space, and so it is uniquely determined by the splitting in the two eigenspaces. I mean, and then we analyze this action. There are two eigenspaces, the ones of the eigenvalues +1, the one of the eigenvalues -1, and the vector space can be written as a direct sum of these two spaces. And now this induces to projection, the projection to the projectivization of one of the eigenspaces and the projection to the projectivization of the other eigenspaces. I would like to call them P plus and P minus. And of course, if I consider the model of X contained in the space, I can project also the model. And so I have a map from X to this projective space and from X to this projective space. Of course, this is, I would like to give a name to the sections of X of L, and some of this section will be contained in V plus, some other will be contained in V minus. The point is that iota acts as identity on all these sections. So the maps defined from X to this projective space is also well defined over the quotients of X, because this is an invariant subspace for the action of iota. And also this one is an invariant subspace because iota X has -1, but we are considering the projectivizations, and so we have two maps which are well defined from X over iota to this projective space. This is pi. And then here I consider this partial resolution. And of course, the maps defined on the singular model defines also a map on these partial resolved models. And the reason is that it's possible that this map just contract the exceptional divisor, but in any case, the map are defined. So we have these two maps, phi plus and minus, which are maps from my Nikulin orbifold Y to some projective spaces. And we would like to understand, since we have everything, we know everything about the neuron-Severi group of Y, we would like to understand if this map are attached to a complete linear system of some divisor. And the answer is yes. I will write the theorem in a moment. I would like to underline that the divisor that I have to consider are a Weil divisor, which are associated to hyperplane section of the image of Y in this projective space, but they are not necessarily Cartier divisor because they could pass through the singularities of my Y, and so they are not necessarily Cartier divisor. And the theorem is the following. So there exist two divisors, the plus and the minus, in the neuron-Severi group of Y, which are, as I said, the Weil divisor and not necessarily Cartier. They are at least co-Cartier, such that we have some properties. The first one is, I first write them and then I try to explain the reason of this, why these conditions are so important. So we have a condition on the push down and pull back of this divisor and a condition on the space of a section, on the dimension of the space of a section of these two divisors. And the promised results is that this map, phi plus and phi minus, are the map attached to the complete linear system of these two divisors. So the first result, this one, is related with the fact that the maps that I defined in the previous page, and I will show you in a moment here, are constructed as follows. I take some of the sections of L in order to construct my maps defined over Y. So I would like that the divisor attached to this map is such that the sections of this divisor are pulled back to section of L, which is exactly what is written here. I take my divisor here, I reconsider it here, and then here, and I find that the sections of this divisor here is essentially a section of the original divisor that I want to consider. The second point is that these two maps are maps to the projectivization of the two eigenspaces. So we expect that this is essentially the dual of V plus, and this is essentially the dual of V minus. And this has to be the dual of V. So of course, the sum of these two dimensions has to be the dimension of the spaces, because we are just splitting the space V into eigenspaces. So this theorem is quite complicated and long to prove. And of course, the main ingredient is to consider a Riemann-Roch theorem on Y. And this Riemann-Roch is a Riemann-Roch on a fourfold, which is an orbifold, on a manifold of dimension 4, which is an orbifold, so which has some singularities. And of course, the formula which allows you to compute this H0 keep track of the fact that the divisors are not Cartier in some points. This result is interesting for several reasons. One of them is that it's not just results on Y, which is quite interesting in any case, because it gives some models of this Nikulin orbifold, but it is also results on X and its involution, because when I know the dimension of this space and of these spaces, I know the dimension of the eigenspaces of the action of iota on V. So I can write down explicitly who is iota on this vector space, and so on the projective space where I am embedding X. And moreover, the fact that these divisors are not Cartier in some points means that points are contained in one of the two eigenspaces. So we have also some information on where the fixed locus of iota on X are with respect to the action of iota on this projective space. So the very last result that I want to mention, which is quite complicated, but I would like at least to mention it, is the following. So if Y, let us call Yx for a moment, a Nikulin orbifold. What is Nikulin orbifold is the quotient of this X by an involution, and then I consider the partial resolutions, and I would like to recall that for this reason I have a class, which is a class of an exceptional divisor contained in Yx. Exactly as we did when we defined the Hyperketer manifold of K32 type, we can observe that there exist deformations that I would like to call just Y of my Yx, such that this divisor is still contained in the second cohomology group of X, but is not contained in the Neron-Severi group of X. So this means exactly that these are deformations which are not really quotients of an Hyperketer manifold by the involution, but just deformation equivalent to this quotient. And what we did was to compute also a Riemann-Roch theorem for this kind of, this Y will be called an orbifold of Nikulin type, just to give it a name. And what we did was to compute also a Riemann-Roch theorem for Y, at least under the conditions that the rank of a Neron-Severi group of Y is 1. And using these results, we are able to compare in a very specific case a model that we are able to give for a Nikulin orbifold and a model for its deformation. So for the complete families of Nikulin orbifold of Nikulin type. And now I just want to write the theorem. So first of all, X is an Hyperketer orbifold of K32 type, such that the Neron-Severi group is a certain lattice, so it is contained in a certain family. And then the divisor D plus, which we defined before, gives a model for this Nikulin orbifold obtained as quotient of X by a symplectic involution. And the model is that the following one. It is we have a 2-to-1 map from our Y to P6, such that the image is a complete intersection of type 3-4, so of a cubic and a quartic. And this model is singular along a surface of degree 48, and this surface is the union of at least two surfaces of something which is not important, plus a surface of degree 16, and this surface is the image under this map of our exceptional divisor. Then we consider the deformation of this construction. So we consider y, which deforms in a specific way yx, and we obtain that there exists D in the Neron-Severi group of these deformations such that we have a map exactly as above, so a 2-to-1 map to P6, such that the image is a complete intersection of type 3, 4, which is singular along a surface of degree 48. And I have to stop here. So there is this splitting. Y is not, this singular surface is not forced to be this union of a surface which is the image of this exceptional divisor sigma, because this is not still a divisor on Y. It's not an algebraic class of Y. So what is changing is just that we have less information on the singular locus, because of course we have something which is a little bit more general. But apart from that, we have exactly the same descriptions. And as I said, one of the main ingredients is that, again, the computation of the Riemann-Roch theorem for this Nikulin, for this orbifold of Nikulin type, and then one has to prove that this map, which is defined here, remains in a certain sense defined after these deformations. And I just want to underline that in general it's quite complicated to give a geometric description even of complete family of Nikulin, of Hyperketer manifolds. And here we are giving a geometric description for a complete family of orbifolds of Hyperketer, which is something which I suppose was never did before. In any case, not for this kind of orbifold. Okay, so I stop here.
Okay, thank you very much. So are there any questions? Comments?
I have a question. So you constructed a new modular space of symplectic varieties of dimension 4, this time singular ones. Could you recall what is the dimension of this modular space?
So of the Hyperketer orbifolds?
Yeah.
Yeah, I mean, you have a construction which is similar to the ones for the Hyperketer manifolds. So you have you have to compute the rank. You have to take the rank of the second cohomology group, and then you have to require that the period has some conditions, and so you have that the dimension in general is 2 less than the rank of the H2, and the rank of H2 is something that is. Yeah.
So in the non-singular case, they all are 20-dimensional.
Is 21-dimensional. Because I mean, you have a 20-dimensional space for the K3 surface, then you have a 20-dimensional space for
But I mean algebraic ones.
Yes, of course. No. Okay.
You introduce a polarization divisor.
Okay. If you assume that if you want something which is projective, then you have 1 dimension less. So in that case, you have to compute the rank of your H2, and you have to subtract 3 and not 2.
And there is a lot of activity around the study of these varieties, whether they are unirational or of general type. And so now you provide a new field. So one can study the unirationality or general type of this new modular spaces of not Hyperketer, but reduced symplectic varieties which are singular.
Yeah, I think it could be interesting. Perhaps something could comes from the studies that were already done for the K3 surfaces, because you have one extra deformations, which of course is a big problem, but I mean, from a certain point of view, the structure of a lattices is always the same. So the point is that how much difference you have when you have these extra deformations, because apart from that, you have everything that it's totally similar to the case of K3 surfaces. But I don't know, even if, because also for the K3 surfaces, the unirationality of some spaces of K3 surfaces, which are quotients by symplectic involutions or not, or admit symplectic involutions, are known and well studied, but in some other cases, it's quite difficult also for the case of a K3 surface if you change a little bit, for example, the order of the automorphisms that you are considering. So it's interesting, but highly non-trivial from my point of view.
For K3 surfaces with the non-symplectic involution, there is a paper of Ma where he studies the dimensionality of 75 different components. So there are 75 cases.
Yeah, that's a non-symplectic case, but yeah, I see.
Okay, are there more questions? Comments? I just wanted to ask you, when we're studying this divisor D at the end, I don't remember, did you say which is the value of D square for the Boville-Bogomolov form? I don't remember you saying that.
Yeah, no, I didn't say.
Two? Or I don't know.
In this case, in this specific case, I think that the form here is something like 2 with a certain divisibility, which comes from with divisibility 2, but I'm not totally sure we will quote them. And the point is that it comes from here. So you have to consider this family, and then you have to go back. This family is something, is okay, you know, is the class of, here we have lambda tilde, where you consider next class, and then when you pass to the quotients, you divide it by 2 the self-intersection. So in this case, it's really a divisor with Bogomolov 2, and in this case, you have some divisibility. You have the same divisor essentially, because you are deforming by considering that divisor to remain a pseudo-ample divisor, in this case to be an ample divisor, and erasing just sigma. I hope I answer.
Yes, and just maybe another quick question about the singularities. When you say so, the quotient, well, you can blow up the K3 and it's still a Hyperketer orbifold, but if you blow up the points, then it's smooth, but it's no more.
Yeah, it's no more Hyperketer because you have some zero on the forms. Yeah. If you want to extend the forms.
So this comes from an explicit computation. You really see, I mean, you have.
I mean, it's a terminal singularities. It's just you compute the age of the action, of a local action. It's terminal singularities. There is no equivalent resolution, so no way to have a trivial canonical bundle and so a symplectic form such that.
And so what is a manifold? If you blow up everything in the smooth manifold, what is it? You know that?
I don't know. I mean, it's just a birational equivalent to what we said, and but it has some zero on the canonical bundle. That's the point. So it remains of quadratic dimension 0, I suppose. But it's just like take a K3 and blow up some points. Okay, it's something.
Yeah. So you don't know. Okay. 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 Thank you. Are there more questions?
Can I ask? Maybe it's a stupid question, but how do you know that? Just I don't know, but when you have phi plus and phi minus, I would have said that okay, maybe they are not completely linear systems, because I would say, since you take the sections
Yeah,
So
the point, the point is that they are defined by a non-complete linear system on X,
okay.
but a posteriori on Y, I find two divisors, which has these nice properties that when I pull it back, I find all the sections of L, and the dimension of the spaces of a section of these divisors is really the dimension of the target space that I want. So at the end, you realize
so you
that
compute the dimension and it's the right one. Okay.
Yeah, we computed the pullback. So we checked that the sections of Y are of a divisor on Y, essentially pull it back to sections of divisor on X. And then we compute the dimensions. And so of these two spaces, and we realized that it's really a splitting of our original space in the direct sum of two objects.
Okay. Thank you.
So more comments or question?
Oh, I have one more comment. So there is also an interesting question about Lagrangian vibrations. So we know that in smooth case, Lagrangian vibrations are dense in the period domain, and there should be something similar in the singular case, but I think that the theory is not finished to say that this is a theorem. So anyhow, it's interesting to understand or to have some examples, some constructions of Lagrangian vibrations on these Nikulin orbifolds.
Not at the moment, but one can try to work out Lagrangian vibration on the quotient by considering Lagrangian vibration not on the quotient. I mean, once again, for the K3 surface cases, it often happens that you have vibration on the K3 surface, which induces vibration on the K3 surface, which is the desingularization of the quotient. So I think it's possible to do this, but I never really tried. So
in Menet's paper, in the paper of Menet, there is an example vibration in prime varieties. Prime surfaces.
Yeah. I have no example now.
Okay, thank you.
Okay.
Any more questions or comments? So otherwise, let's thank Alice again. Thank you very much.
Thank you. Thank you to everybody, and thank you to the organizer, of course. This is the moment. Thank you, organizer.